Okay, class. A couple of announcements. Today we'll finish the lecture on the on steam turbines easily. We don't have too much more to do. The video I have queued up here, we're going to watch half of it today and half of it next time. And a week from today, you're going to have your test on boilers and steam turbines. So your test will be in iLearn. It will be true, false, multiple choice. I have to go back and take a look. I don't recall any calculations. If there's any calculations, I'll give you a heads up. We just haven't done much on calculating anything on boilers and turbines. So it's pretty much all informational stuff. And these two turbine videos will potentially be on there, but I mean, I realize there's a tremendous amount of detailed information here, and I'm not going to ask you little minutia off of these videos. If there's something I consider a big concept and something that we've also talked about in class, then I think that's fair game. But I mean, you get into the details of some of these hydraulic control systems and all that, that's really down in the weeds. And I mean, I've been known to be mean, but even I'm not that mean. You know, I'm not going to do that to you. I'm not trying to just persecute you. But I do want you to watch these. We'll watch the first half of this one in class today, and then the second half next time. So actually, the end of this video will be the end of the material. But as far as in-class lecture, that I do will wind up today. So it's boilers and turbines, and it's a week from today in iLearn, and you'll have the whole period. I'll turn it on, and you know, you'll have the class period to do it. Okay, and there's a big message at the start of this that unlawful use is punishable by fines and prison, but I think they'd have a hard time for me recording this in class. So I'm gonna be brave and go ahead and record it anyway. Y'all come visit me in the slammer. I got to check I got to get my audio settings. I almost forgot. Make sure that we're right. Manage. Yeah, we're not on HDMI. Okay, looks like that's permanently set unless I change it back. Okay.
Sorry, can you repeat the thing about the test? I wasn't able to write it down.
About the test? It'll be a week from today. It's on boilers and turbines, and it will include these two turbine videos in a general sense. I will not ask just stupid minutia off of these, but if it's a concept we've also talked about that gets reinforced on the videos, then I probably will be sure to ask something about it. It'll be in iLearn, and you'll have the whole class period.
Okay, great.
Okay, now let me get all my volume set here. Make sure everybody can hear. Okay, got that.
In the previous module, we looked at the main features of turbine construction and the essential support systems. Now it's time for us to turn our attention to steam turbine operation and control. And we'll begin by looking at the means of adjusting the turbine speed or turbine output. The principle of turbine control is very simple. If we need to increase the power output of the turbine, we have to pass more steam through the turbine. Conversely, in order to decrease power output, it is necessary to decrease the amount of steam admitted to the turbine. Turbine steam flow is controlled by adjusting the turbine admission valves, or control valves as they are often called. In the most simple arrangement shown here, we have one control valve, which, depending on its setting, allows more or less steam to flow into the turbine from the steam chest. When the turbine stop valve is open, the steam chest is charged with steam directly from the boiler. In most turbines, multiple control valves are used as shown here. In this particular arrangement, the steam chest is located above the high pressure end of the turbine shell. We can see here 8 valves, and these are opened in sequence according to the position of the cross arm, which is itself adjusted by the hydraulic control system. These control valves are set in such a manner that only one valve at a time is actually throttling steam, while the others are either fully open or closed, depending on the actual load. The result is that the throttling losses are smaller than in the case where only one large control valve is used. In large machines, say greater than 100 megawatts, it is more common to have 2 steam chests, one above and one below the shell, or located one on either side of the turbine. In this case, multiple control valves are located in each steam chest, with steam lines connecting to the turbine shell at the high pressure end. In most arrangements of this type, a stop valve is fitted at the entrance to each steam chest. During normal operation, the stop valve remains in the wide open position, while the control valves are modulated to adjust steam flow. The actual opening of the control valves is determined by the position of the operating lever, and this in turn is adjusted by the power cylinder of the hydraulic control gear. This schematic shows us a simplified version of a hydraulic control scheme. In this particular arrangement, a mechanical governor is used to sense turbine speed. Other types of governors are also used, as we'll see in a moment. In this configuration, a change of turbine speed causes the centrifugal weights to move. For example, a decrease in speed causes the centrifugal weights to move inwards and lower the pilot valve. This, in turn, allows more high-pressure oil to enter the power cylinder and raise the piston against the compression spring. This movement of the power piston opens the steam control valve and allows more steam to enter the turbine, which causes its speed to increase. Also known as the power piston rises, the reset lever lifts the pilot valve back into the neutral position again. On large turbines with multiple control valves, a considerable amount of power is required from the power cylinder. In this case, it's usual to employ a double relay type of pilot valve. In this arrangement, we have high pressure oil above and below the piston. Now, when the position of the governor spindle changes, say for an increase in speed, the pilot valve lifts and allows high pressure oil to flow into the space above the power piston. At the same time, the pilot valve exposes the space below the piston to the oil drain and returns the oil to the tank. The high pressure oil above the piston pushes it downward and consequently moves the control valve in the close direction. At the same time, it also moved the reset lever to bring the pilot valve back to neutral position and so prevented further movement of the control valve. Now let's take a closer look at the governor itself. This mechanical type centrifugal governor is driven directly from the turbine shaft through a gear drive. As speed increases, the weights fly outward due to centrifugal force and lift the sleeve against the compression spring. The sleeve itself is connected to the pilot relay, which in turn adjusts the control valve through the hydraulic servo mechanism. We can adjust the set point of the governor by adjusting the compression on the spring. The adjusting nut moves up or down according to rotation of the screw thread. This action can be performed manually at the turbine, or as is more usual, from a remote position by operation of a small motor drive known as the speeder gear. This name derives from the fact that when the turbine generator is not synchronized to the power system, any adjustment of the governor set point will indeed alter the speed of the turbine. However, when the turbine is on load and the generator is synchronized to other machines, any adjustment of the speeder gear produces an imperceptible change in generator speed. Instead, this action causes a change in steam flow through the turbine, with a consequent change in generator output. We'll be talking more about characteristics of the governor and its effect on the electric power system in the next module. Another type of governor used on many machines is the hydraulic governor. In this arrangement, a governor pump fitted to the front end of the turbine shaft is designed to be extremely speed sensitive. As the turbine speed changes, so does the oil pressure output from the pump, and this in turn is used to adjust the position of the pilot valve on the power cylinder. As before, a set point adjustment is provided to allow control of the governor setting and consequently the turbine output. On modern machines, it's more common to use an electronic type of speed sensor and an electro-hydraulic governor. In this arrangement, a toothed wheel is fitted to the shaft. An electronic sensor measures the pulse rate produced by the toothed wheel, and from this calculates the turbine speed. The electronic signal is then processed and converted into a mechanical output that then operates the pilot valve in the normal manner. In these governors, the set point and other adjustments are, of course, inputted electronically to the processor. All of these different types of governors still require high-pressure hydraulic oil to actuate the power cylinder and consequently provide movement to the turbine control valves. The same hydraulic oil supply is used to operate the turbine stop valve. One common arrangement is shown here. During normal operation, the pilot valve is open and allows high-pressure oil to enter the space below the piston and hold the stop valve open against the compression of this high-powered spring. In order to close the stop valve, the pilot valve must be moved to the trip position, thereby allowing the high-pressure oil to drain back to the oil tank. As a result of the sudden decrease in oil pressure below the piston, the compression spring slams the valve closed. As we'll see later, operation of the pilot valve, or trip valve as it is known, can be achieved by any one of several alternative means, including a manual trip, a remotely operated solenoid trip, or a trip signal from various protection devices. On reheat turbines, an additional stop valve and control valve are located at the reheat steam entrance to the intermediate cylinder. We can see the arrangement here. The reheat stop valve functions in the same manner as the turbine main stop valve, and in fact, its operation is triggered by the same trip mechanism. So in normal operation, this reheat stop valve is retained in the wide open position, similar to the main steam stop valve. If we wish to trip the turbine under any emergency condition, the trip relay is operated and closes both stop valves immediately. If there were no reheat stop valves fitted, then the large amount of steam that is contained in the reheat piping and reheat tubes in the boiler would continue to flow to the reheat turbine for a short period of time and perhaps cause a turbine overspeed. In other words, we would have no control over this relatively large quantity of entrained steam. The reheat stop valve prevents this from happening. Similarly, the reheat intercept valve is fitted to assist in precise control of the turbine. The intercept valve is in fact a control valve that normally remains wide open, allowing all of the turbine control to be carried out by the main steam control valves. However, in the case of a partial load rejection, perhaps due to a transmission line trip, operation of the main steam control valves by governor action may not be sufficient to hold the turbine speed down. Again, this is because of the entrained reheat steam continuing to pass for a few minutes through the intermediate and low pressure turbines. The intercept valve prevents this. It acts in conjunction with the main steam control valves and actually starts to close in anticipation if the turbine speed rises to 2% above normal. A similar problem can occur with entrained steam feeding back into the turbine from extraction lines. To prevent this, positive closing non-return valves are installed and arranged to close when the turbine is tripped. The valves are actuated pneumatically but are controlled by a hydraulic trip relay. So we can see that our hydraulic system does have an extremely important function to fulfill in operating the turbine. A high-pressure oil pump feeds hydraulic oil to control valves, that is main steam control and reheat intercept valve, emergency stop valves on the main steam and reheat lines, and a trip relay for extraction line non-return valves. Much of the equipment that we have been discussing is contained in the front end pedestal of the turbine. In fact, this is often called the governor pedestal. In this schematic, we can see the main oil pump driven directly from the turbine shaft, the power cylinder, which operates the control valves, the centrifugal governor and its pilot valve, an intermediate power cylinder between the governor pilot valve and the main power cylinder, the hand wheel for manual operation of the speeder gear, a load limit hand wheel, which can be set to restrict the turbine output, and the trip relay, which operates the stop valves. We can also see several devices which actuate the trip valve, such as the hand trip, the solenoid trip, and the overspeed trip. Now, at this point, let's take a break, and then we'll come back and look at a typical turbine startup. For now, please switch off the tape and review this material in your workbook.
Okay, I just want to make a quick comment here. It's interesting to me that when the unit is synchronized and tied to the grid, you basically can't change the rotational speed when you're putting steam through it because it's in sequence with all of the other turbines, and there's a tremendous amount of inertia out there. And so what happens if you do anything that changes the steam flow through the turbine, you simply change the amount of megawatts that are produced. So now, if you're not tied to the grid, then you have that governor has to function in order to control the speed. Interesting.
In this segment, we're going to look at the actions taken by the operator to perform a typical turbine startup. Of course, we all know that there are different arrangements of turbines and control equipment, but the basic requirements for a startup are the same. Even before we think about admitting steam to the turbine, there are a number of very important maneuvers that must be carried out. If the turbine is returning to service after a long outage, then the first thing we must do is to place the unit on turning gear. This entails running a low-pressure oil pump to circulate oil through all of the turbine and generator bearings, and starting the hydrogen seal oil system. The turning gear motor can now be started to rotate the shaft at low speed, usually about 10 RPM. The procedure for charging the generator with hydrogen is detailed in the next module in this series. This maneuver takes several hours to complete, so it is clearly necessary to get an early start and plan the complete operation when returning a unit to service. During a short shutdown, say overnight or even for a few days, it is normal to leave the generator rotating on the turning gear and to keep the generator charged with hydrogen. Of course, if the generator is air-cooled, then we would not be faced with hydrogen charging. However, there is another more vital reason for keeping the unit turning over when it is taken off load. Remember that the internals of the turbine are extremely hot. If we were to leave the rotor stationary immediately after shutting the machine down, experience shows that as the heat rises to the upper part of the rotor, it causes uneven expansion and distortion like this. This is known as hogging, and in some cases, the bend may be so severe that the rotor will not recover its original profile even after cooling. Imagine trying to start this machine when there may be contact between moving and stationary parts of the turbine. To prevent this problem, it is essential that the rotor be placed on turning gear immediately after the unit is taken out of service. This ensures that the heat is evenly spread around the rotor and there is consequently no chance of distortion. It should remain on turning gear for several days at least if a long outage is contemplated. Operation of the turning gear after shutdown is so important that in the case of a failure of the equipment, say a motor failure, then drastic action must be taken. One method adopted on smaller machines is to rotate the shaft by hand, if possible, say 180 degrees every half hour. On older machines, this was sometimes achieved by inserting a bar into the coupling. Thus, the first types of turning gear were often known as barring gear. On larger machines, this is not possible, and the only real solution for a failure of the turning gear is to admit steam once again to the turbine and run it up to speed. Well, that's enough about shutdown. We really want to talk about startup procedures. It's evident that in most cases, we'll find the turning gear already in service with lube oil circulation. The generator hydrogen cooling system will also be ready for operation, and we'll be talking more about this in the next module. The next thing we must do is make sure that we have steam at the turbine stop valve and that the stop valve drains are open sufficiently to allow any condensed steam to be discharged from the pipework. We'll be discussing the procedure for charging steam lines in another module. Once the main steam line is charged to full boiler pressure, it is now time to charge the steam chest by opening the turbine stop valve. Most modern stop valves are equipped with an internal bypass, which allows a small flow of steam to enter the steam chest in order to raise the metal temperature at a controlled rate. Of course, the stop valve drains will be retained fully open during this maneuver. Eventually, when the steam chest is fully charged, the stop valve will be opened wide and the stop valve drains throttled in. During this period of time, the circulating water system should be started up and the flow of water established through the condenser. We can also begin to draw a vacuum in the condenser by extracting all of the air. Before beginning this activity, it will be necessary to put the gland steam system into operation to prevent air from entering the turbine at the shaft seals. The vacuum pumps or startup ejector are placed in service, and we can observe the indicated decrease in back pressure from atmospheric, about 30 inches of mercury, down to say 2 or 3 inches. Summarizing then, the following conditions must be established before steam can be admitted to the turbine. Lubrication system in service. Turning gear in service. Generator hydrogen system in service where applicable. Circulating water flowing through the condenser. Gland steam system in service, providing sealing steam. Air removal equipment in service with vacuum established in the condenser. Steam line from the boiler charged and turbine stop valve open to charge the steam chest. Stop valve drains and steam chest drains open to ensure removal of any water, that is condensate, and all protective devices reset and available. In this condition, one method of admitting steam to the turbine and running it up to speed is to operate the control valves by manual operation of the hydraulic control system. In bringing the turbine up to speed, relatively little steam is required, and it is probable that only one or at the most 2 of the control valves will be open or partially open to control the rate of speed increase. This feature has a particular negative impact. For example, looking at this overhead steam chest, we see that each of the 8 control valves supplies steam to just a small arc of the admission nozzles. Consequently, with only 1 or 2 valves open, there would be a tendency for uneven heating of the turbine block. And this could perhaps lead to distortion and eventual cracking of the metal. Even with the side-mounted steam chest, we still have the same problem. In this arrangement, each of the 4 control valves supplies its particular arc of admission nozzles. So the same problem of heat distortion still exists. This method of control is known as partial arc admission. Of course, when the turbine is on load, more of the valves are opened, thus providing more even heating of the nozzle block. On large turbines, this problem is particularly pronounced, and startup is usually performed in a different manner, that is, by full arc admission. In this case, the stop valve is closed after heating the steam chest. Then the control valves are all opened completely, providing access to the complete 360 degrees of admission nozzles. Steam flow to the turbine is then controlled by throttling at the stop valve. This may be carried out by manual operation on a hand wheel like this, or perhaps remotely from the control room. With this arrangement, the turbine governor takes control by throttling the control valves as the turbine speed approaches its normal operating level. The stop valve should now be opened wide, and the governor set point can be adjusted so that the control valves raise the speed to the nominal 3,600 RPM or 3,000 RPM, ready for synchronizing. When the generator is synchronized and the turbine is on load, the steam flow into the turbine will be controlled by the control valves according to adjustment of the governor set point. Once the unit is on load, the stop valve drains, steam chest drains, and turbine shell drains can all be closed. How long should this startup operation take? At what rate can we raise the turbine speed during startup? Well, this all depends upon the prior condition. That is, how long the unit has been shut down. In other words, is it hot or cold? When we first admit steam to the turbine, it is rotating on turning gear. As soon as the speed starts to rise above turning gear speed, this device is automatically disengaged. At this point, the operator will shut down the turning gear motor. When the turbine is undergoing a cold start, we must allow sufficient time for the various internal components to be heated by the steam flow and expand as uniformly as possible. As shown by this typical startup chart, it may take several hours to bring the cold unit up to synchronizing speed. The manufacturer normally provides startup charts showing the manner in which speed should be raised for different startup conditions. Make sure that you have a copy of the startup curves for each of your particular turbines. Where the unit is undergoing a hot startup, perhaps after an overnight shutdown, the turbine speed can be raised quite quickly within about 30 minutes. The unit can also be loaded quite quickly. The reason for this is that the turbine metal is already hot, probably around 800 degrees Fahrenheit at the steam inlet. Ideally, we should provide steam to the hot turbine at or above that temperature to prevent cooling and the subsequent reheating. This is not as easy as it sounds. In order to raise the steam temperature, we need to fire the boiler harder. But we cannot do that without having an increase in steam flow from the boiler. Even with all of the superheater drains and all of the reheater drains wide open, it may not be sufficient to provide the desired increase in steam temperature. In units which are installed specifically for two-shift operation, a steam bypass arrangement may be built into the system to permit this increase in steam flow during startup. As we see from this schematic, the bypass system allows us to increase steam flow through the boiler, bypassing the turbine. The excess steam is dumped into the condenser, where it is cooled by the circulating water. Of course, there is a heat loss involved, but we do achieve the objective of providing a hot start and improving the life cycle of the turbine. During the run-up of the turbine, care must be taken to avoid as far as possible the critical speeds. Now, what do we mean by this term, critical speed? Well, this refers to a specific speed at which very high vibration occurs due to natural resonance of the turbine. If the rotor is allowed to run for any length of time, even a few minutes, at a critical speed, the vibration would be great enough to probably shatter blades and perhaps other components. In order to avoid this situation, we must pass as quickly as possible through the critical speeds during the run-up. But what are these critical speeds? Well, as our rotating mass is made up of several rotors, for example, the high pressure and low pressure turbine rotors and the generator rotor, we may have several critical speeds. The specific speeds will be indicated by the manufacturer. And in fact, the run-up curve provided will make sure that the rotor is not allowed to dwell at any one of those speeds. If you have an automatic startup on your machine, no doubt the run-up program will ensure that the unit passes through these speeds as rapidly as possible. When the machine is first synchronized, it should be loaded immediately to its established minimum load, usually 5 or even 10% of full load capacity. One reason for this is to make sure that there is sufficient steam flow to keep the low pressure blades from overheating. At very low steam flow, there exists a real danger of overheating due to friction and consequent damage to the very large LP blades. The speed of the outer periphery of these blades approaches the speed of sound, and this creates tremendous friction even under near vacuum conditions. In fact, some turbines are fitted with exhaust hood sprinklers, which are activated if the hood temperature rises above 180 degrees Fahrenheit. Another more mundane reason for loading to about 10% is to allow all of the automatic control systems to be brought into service and stabilized. Now at this point, let's take a break to give us time to reflect on our discussion before moving on to look at other operating precautions that must be observed. At this time, then, please switch off the tape and thoroughly review this material in your workbook.
Okay, that's pretty much perfect timing for us. So we'll cut this guy free for today, give him the rest of the day off, and we'll go ahead and try to finish the rest of the turbine article. I'll tell you, I discovered these videos, I don't know, 3, 4, 5 years ago. And I must say, they just dovetail so well with the material in this class. And he's got a whole series of them. He's got them on boilers and all kinds of stuff. I mean, we can't listen to all of them, but this intermeshes with the turbine article pretty well. So I'll make a point to cover these couple. Okay, so this is where we finished off last time. What is this? The bottom of page 16, I believe. Yeah. Okay, and so the discussion up above was, I think, on motoring and anti-motoring. You know, if the turbine steam valve was to close by mistake at very low loads and the unit was synchronized, then that generator would become an induction motor or a synchronous motor, and it would actually turn the turbine train, and that would cause overheating very, very quickly. It's amazing how quick this stuff can generate heat. But of course, 3,600 RPM is pretty quick, and he was talking about the near sonic velocities of the LP blades because of their length. So now we'll go on to a different situation, related but not the same. So another low load operation is that we've talked about was carrying auxiliary load, following a separation of the unit from the system load. So what we're talking here, and he makes it clear later, is that this is an electrical trip. So it's like we haven't tripped the turbine, but something happened and the generator got tripped and it's no longer synchronized to the rest of the grid. And so when that happens, we've got to dump load immediately because station load is not nearly that big. And so this thing is going to fall almost instantaneously down to like 3 to 5% load. And so that's the situation he's talking about here. So low load operation carrying auxiliary or station load following separation of the unit from the system load. In this case, motoring can't occur because you're not tied to the grid anymore. But we can still worry about overheating the low pressure exhaust end blading. And then he goes into the thermal stress discussion here. In addition, the transient thermal stress in the high pressure rotor is a factor to be considered when suddenly dropping from full power tied to the grid to auxiliary station load and subsequent reapplication of load after the connection to the system is reestablished. So it could be a fairly short-term situation where all of a sudden, whatever caused you to trip, it gets cleared, and you can then make sure you're in phase and reconnect to the grid, in which case then you would want to go back up in load pretty quickly. So this is probably the most potentially damaging type cycle that we've talked about in terms of the turbine. The immediate effect on the fossil turbine, for example, is an instantaneous drop in first stage steam temperature of about 250, followed by a further decrease of 200 in about 15 minutes as the superheater outlet temperature adjusts to the newly established firing rate. Because, you know, I mean, we got to cut the boiler back to just about nothing. And so that's 450 degrees within about 15 minutes. Whoa. I mean, come on, guys. That's pretty aggressive. So this drop in first stage temperature produces a peak stress in 10 to 15 minutes after the initiation of the transient, which decays slowly to zero in about an hour. If auxiliary load is maintained for an hour or more, well, so at auxiliary load, we're at 3% boiler load, we're going to have cold steam because of the boiler droop, okay? And so if you maintain that low auxiliary load for an hour or more, then the rotor is force cooled to a new equilibrium state. So however cold that steam is, after an hour, it's going to basically cool the rotor to that temperature. The subsequent reloading should then be performed at a very moderate rate. So then, say you run on station load for an hour or two, cool that rotor down. They say, "Okay, guys, we're ready to go. We just synchronized. Let's go. Let's make some megawatts." And you're sitting there, go, "Whoa, now hold on, we got to slow this puppy down." Because the subsequent reloading should then be performed at a moderate rate in order to avoid large thermal stresses in the opposite direction. Wow. Never knew engineering could be so exciting, did you? For a typical 3600 RPM rotor, peak stress can be expected to initiate cracking for this type of a severe cycle in the rotor after 100 to 400 cycles of complete stress reversals. A single cycle of this magnitude would therefore account for approximately 1/4 to 1% of the total fatigue capacity of the rotor. So you can eat up 1% in one event. Pretty extreme. Full load to auxiliary load transients will reduce the total fatigue capacity of the rotor for normal load changes, but this reduction is not excessive unless many such transients occur. Yeah, like you don't want to be doing this every day, you know. Or if you do a lot of this, you're gonna trash this rotor pretty quick. To minimize the accumulation of rotor fatigue damage, it's recommended that auxiliary load operation following an electrical trip out occur only when system conditions make it absolutely necessary. So if you trip this thing electrically, you got a hot rotor, you don't want to sit there and force cool it with cold steam. You'd be better to bottle it up and let it sit there than to put it on auxiliary station load. But guess what? There's an additional problem associated with the rejection of 95 to 97% load, followed by offline operation at 3% to carry station auxiliaries. The problem is the rapid cooling of the high pressure turbine rotor in comparison with the much slower cooling of the very heavy high pressure inner cylinder. So the rotor is going to cool more quickly than the inner cylinder. And so we have the possibility of differential expansion that can lead to rubs under this 3% operation. That heavy axial rubs can occur with possible serious damage to equipment. And then there's a comment here about nuclear. interesting. Nuclear, the steam conditions are far less. It's not that far from saturation and all. So nuclear units designed to accept 100% system load rejections and then carry auxiliary station load, including reactor coolant pumps. The internal temperature changes that occur in the high pressure turbine are not as great as those described above for high temperature fossil unit. Auxiliary load is sometimes as high as 10%, which lessens the LP heating concerns, but the effect on high pressure rotor fatigue life must still be considered. So nuclear just don't operate at the same extreme temperatures and pressure, so they are more forgiving, but still considerations must be made. Okay, next topic, feed water heaters out of service. You know, I mean, you understand feed water heaters, that's the regenerative portion of the Rankine cycle. We want to boost that feed water temperature before we get it back to the boiler, because that raises the average temperature during the heat addition in the boiler. Okay, so we all remember that from our thermo review. So it may be necessary at some time during operation of a unit to take an individual feed water heater or sometimes a bank of heaters out of service, depending on how it's set up. Reasons for such action might be the flooding of a heater due to a tube leakage. You know, these things are just big shell and tube heat exchangers, big ones. I mean, probably they're about as big as this classroom, is long, maybe 7, 8, 9 feet diameter. It's just a big heat exchanger. And they're going to have tube leaks from time to time. So that could be one reason. Might be, let's see, tube leakage or due to a drainage problem. Boiler problem necessitating reducing the temperature of feed water entering the steam generator. Condensator feed water pump problem, which necessitates bypassing heaters on the water side. Or this last one is, I think, the most interesting. The rest of them are pretty mundane. Or to get an increase in megawatt output during a system peak load period by removing the top or highest pressure heater. So you take the high pressure heater out of service on purpose. Well, what happens? So remember, that's your highest extraction point, pressure extraction on the high HP rotor, right? Goes to the highest pressure, highest temperature feed water heater. So that leaves that steam in the turbine. So, you know, we've seen numbers like 30, 40, 50, 60,000 pounds an hour of steam that you leave in the turbine instead of taking it out. Well, guess what? So then you are putting more than the design capacity of steam through the entire remaining portion of the turbine. So you put more steam, you push harder, what do you get? You get more megawatts. Of course, this may not be good for your efficiency and it may not be terribly good for your turbine, but for short periods of time, it can be done on purpose to get more megawatts. That's kind of interesting. If one or more heaters are taken out of service and the turbine throttle flow not changed, steam flow increases in the blade path downstream of the inactive extraction point, since the steam normally extracted now remains to flow through the turbine. The kW output will increase as a result, and the thermal cycle efficiency will decrease because you're pushing these blades harder than they were designed to be pushed. And so they're going to lose efficiency. Such operation distorts the normal flow, pressure distribution, and work distribution throughout the turbine. These parameters are the major factors that determine the stresses placed on turbine blades. If the unit is being operated at or near maximum capability with heaters out of service, it may be necessary to reduce throttle flow to produce more normal conditions in the downstream blading to prevent exceeding design and eventual blade damage. So turbine manufacturers provide guidelines. So, you know, if you're gonna have to have that increased steam flow for any length of time, you're gonna have to reduce the throttle flow so that you keep you know, you might do it for an hour or two in an emergency situation, but you're not going to do it for very long. Operating with one or more heaters out of service while a higher pressure heater remains in service is shown in figure 15. Let's take a look down here at figure 15. There you go. So they're showing 3 extractions and 3 heaters just to simplify the diagram. So in this case, it's the middle heater that is shut down. Okay. Well, so another thing that's going to happen is the high pressure heater is going to experience a higher than normal extraction steam flow. Because see, at this point in the turbine, right here, normally we would be pulling out, say, 50,000 pounds an hour. Well, that stays in, which then increases the pressure. You know, that's going to increase the pressure distribution all back through this rotor because you're cramming that additional steam through these blades, but that's going to affect the pressure upstream. And so if you have a higher pressure at this extraction port, that's going to force more steam into the #1 heater, and you're likely to have problems with the #1 heater because of that additional steam flow. So not only do we have the problem of additional steam flow down through here through the blades, which can overstress blades, we also can force more extraction steam down into the higher pressure heaters, which can cause them problems. Okay. Let's get this set up again. Let's see. Reference to 15. Can't find where I was now. I'll find it. Good water heaters. There we go. And that's where, right after this, where it says figure 15, that's where he's talking about this. Depending on the number of heaters removed, can result in greater than design extraction flow to the higher pressure heater in service, overloading the steam side of the heater and increasing pressure drop in the extraction pipe. So in addition, turbine blade path conditions are upset, so blah, blah, blah. Additional jobs. So we may have to adjust the throttle flow. Okay, so that's the end of feed water heater out of service. And so for the test, you know, I might ask you, you know, about some of those different conditions. You know, what would happen if we took, you know, a high pressure heater out of service? We get more megawatts. Would it be good? Maybe for a little while before things started breaking, you know, etc. Okay, so the last topic, yeah, we got plenty of time. We'll get this thing finished today, is water induction. And this first couple of paragraphs is talking about different committees and all that stuff. So water incidents have plagued the industry for a long time. So we'll pick up here. Many go undetected or unreported because no significant damage, at least can be determined without opening the turbine, has occurred. Others, you know, we find at inspection, and a severe incident will knock the unit completely out of service quickly. So we can characterize those as 2 types. water inducted from outside the turbine, or water accumulated within the turbine. So water induction is the most common, and it's fluid or cool vapor being induced into zones of the turbine from a source external to the turbine. So water accumulation is the accumulation of basically condensate, condensed steam, in some zone of the turbine. Maybe it collects to the point that it just gets too much. You get a load increase in steam velocity, and it pulls a big bunch of that water through the turbine in the liquid state. Most common type of water incident occurs on fossil turbines when water is induced into heated turbine components, causing distortion and rubbing. So you can get such cooling effects that the differential expansion causes you to basically wreck, or you get those rubs, and rubs are extremely damaging. Probably the most distressing type of water incident is the induction of water into the base of the high pressure or intermediate pressure turbine when it's running. Figure 16 we'll go look at. Let's read this and then we'll go take a look at it. So what happens, this cool water goes into the base of the turbine, and it basically draws up relative to the rest of it, and it causes the thing to kind of hump over, is the term they use here. And it moves stationary parts into the path of rotating parts. Heat produced by rubbing can and has melted and fused turbine components together and sent molten metal through the blade path. That must have been an exciting day in the plant. Not necessarily a fun one. You know, my old buddy Mike Stakely, who was in the turbine division of TVA that worked in Chattanooga, I worked with Mike a lot, and he told me one time, I forget which plant it was, but they started a unit and the hydraulic pumps weren't working or went out during the start. And nobody knew it, so they weren't supplying any oil to the journal bearings. So this thing was running metal to metal contact for a while. And they did it, they started this thing up, I don't know, 30, 45 minutes later, they noticed some strange vibration. And it got fairly severe for 10 or 15 minutes, and nobody knew what it was. And they said, well, let's see if we can just get through it. Well, after 10 or 15 minutes, it kind of planed out. And they went on up in speed, and everything ran pretty well for another, I don't know, 30, 45 minutes. And all of a sudden, the journal bearings just flew apart. And what had happened is it had run, that vibration is when the steel was melting. And so then they got a nice cushion of molten metal. And the bearings ran, instead of on hydraulic fluid, they ran on molten metal for another 30 or 40 minutes before it was just an unsustainable situation. And the bearing seized up and it just wrecked the unit. And that unit was out for, I don't know, 6 months, a year before they got all that mess cleaned up. But anyway, the stories they can occasionally tell about things that have gone on in the old power plant. Okay, let's go down and look at this 16. Okay, and this isn't much, but anyway, so this is how we would normally operate, and you get cooling water induced into the base of this thing, and it basically causes it to cool and contract while this is hot, and it causes this distorted shape that then puts the blades in contact, stationary and rotating, which obviously is a pretty bad thing. Not good. There we go. Okay. The major problem with nuclear units with regard to water incidents is the accumulation of sufficient water from external and internal sources to cause contact between blades. the blades and the water. Direct mechanical damage will occur because the steam in the nuclear turbine is near the saturation point. Detrimental quantities of water can accumulate without large changes in cylinder temperatures and expansions. Quite possibly the first noticeable indication would be rotor vibrations. Therefore, detecting water in nuclear units can be more difficult than fossil units. So once water enters the turbine, extremely unlikely that all damage can be prevented. Possible damage by water includes, but it's not limited to, blading and shroud failures, thrust bearing failure, rotor cracks, blade ring cracks, permanent distortion of stationary parts, and crushed blading gland seal strips. The degree of damage is a function of many factors, including point of entry, quantity of water, length of period, metal temperature changes, speed and or load on the unit, steam flow, relative position, on all this stuff. So, I mean, it's pretty complicated as far as trying to figure out exactly what's going to happen. So many factors are involved that no single set of operating instructions will be adequate for every incident. In many cases, damage can be minimized if prompt decisive action is taken at first warning of water induction into the steam turbine if they can figure out what to do. Majority of water incidents occur during transient conditions, shutdown, startup trips, large load swings, but can occur during steady state. This is where water can be induced from, because these are vessels that normally contain water, boiler, feed water heaters, tanks associated with our cycle, deaerator, storage tanks, etc. Miscellaneous tanks, such as startup flash tanks on a once through. Systems with access to water, superheater sprays, reheat attemperating sprays. We talked about those attemperators, why they put them in between the sections of the superheater. So if one of them fails, they have a chance to vaporize a lot of that water before it gets into the piping, before it works its way down to the turbine. Gland system sprays, condensate system, and the exhaust hood sprays, which we hadn't talked about, which we saw in the video just a minute ago, to keep those LP large blades from overheating at the end of it. Systems that are sources by virtue of accumulating condensation could be main steam piping, hot cold reheat piping, plant extraction piping, turbine main steam and reheat piping, and turbine cylinders. And the primary sources of water causing incidents based on frequency of occurrence are. So this to me is kind of the pretty good information. I mean, where are we most likely to get the water from that's going to cause the water incident? Okay, feed water heaters or extraction systems, number one. Boiler and main steam system, number two. Reheat attemperators, failing, spraying too much water, number three. Improperly drained steam pipes or improperly operated drain valves, operator error. Oh, that's nice. And startup cycles of once through boilers, but there's not all that many once through boilers out there. Okay, so I think that's about as much of this. I've pounded you pretty good on this. You can read over the last of it, but I'm not going to present any more of it in class. We're on 23. There's a couple more pages here, but I think this pretty well gets the point about water damage and what happens if we get liquid water into the turbine or accumulated into the turbine. Okay, so nah, I can't let you go with this much time. So our next, and I sent you an email today, a while ago, and let's see. So we're going to do a little block on combustion, because this will review your combustion principles. And, we're talking a lot about burning fossil fuels in here, and combustion is what it's all about. And that that lecture we looked at from that guy at MIT on carbon capture and sequestration, that is really an interesting topic related to the power industry and combustion and all that sort of thing. Because the more you travel around the country, the more plants you go into, the more you realize the unbelievable amount of infrastructure that is in place, not only in our country, but the world, that's tied to fossil fuels. It's just not going to be easy to get off of fossil fuels. I mean, companies are going to have to make unbelievable investments if they're going to go to like electric heating equipment. And electricity on a delivered energy basis is far more expensive. So products are going to go up in cost. And I mean, just the amount of change in our industrial sector and our society and our cost structures is going to be unbelievable. And so that presentation that talked about carbon capture and sequestration, if that can be done effectively and cost effectively, then all of this equipment base that's tied to fossil fuels can continue to be operated probably into its useful life, because a lot of the stuff's been out there, so it may have a useful life for another, 5, 10, 15, 20, maybe 30 years max, because I mean, everything wears out and has to be replaced. So if you could do cost-effective carbon capture sequestration, make a carbon-based product or do something to mitigate the majority of the carbon emissions, then these fossil fuel sources could continue to be used. I mean, nobody really cares about digging carbon out of the ground. They just don't want to put it all in the atmosphere. So if we can dig it out of the ground, burn it for the energy, and then capture it and turn it into a product, I think there's some people going to object, So as we say, some people complain if you hang them with a new rope, I mean, somebody's going to complain no matter what, but it takes a lot of teeth out of the climate argument if you can capture the carbon. Because the rest of the emissions, we do a pretty darn good job of. As you guys will find out more and more as you get another STEAM chapter to read, which I know you look forward to. So we'll get to that. I'm trying to not pound you to death on the STEAM chapters. They are pretty onerous. So anyway, I mean, some people may looking at some of this stuff as studying yesterday's technology, but I'm not sure that's the case. It could be the case. It could be that we can't do effective carbon capture sequestration, and all of this vast collection of fossil burning equipment is going to have to go away, but it just can't go away that fast. I mean, there's just too much out there. So anyway, I'll get off my soapbox. So let's look a little bit at the principles of combustion. So, combustion basically is oxidation. And in the fossil fuels, we're really talking about burning three things: carbon, hydrogen, and sulfur. If it's present, we would just as soon it not be present. But if you're burning some of these coals, you can't get away from it. You can buy low sulfur coal, but there's still some in there. And at the limit that sulfur dioxide emissions have been ratcheted down to, if you're burning much coal, you're going to have to clean up your emissions. Okay. And of course, every time we clean up emissions, that usually takes energy. So the auxiliary load, the station load goes up and the efficiency goes down. And the cost goes up because these systems are multi-hundreds of millions of dollars, if not billion-dollar projects. Those of you that go to Kingston, we are going to go to Kingston. And by the way, if you haven't sent me your name, go ahead. I'm about to send the list to Kingston. I mean, I could add names later, so that's not a problem, but go ahead and let me know if you're going. But they spent like $1 to $2 billion there, I don't know, 10, 15 years ago on sulfur scrubbers and all that stuff. And I mean, it's huge equipment. I mean, golly, the whole place. And Kingston doesn't even have big units, and it's still huge. I mean, some of these places are just unbelievably large. But I mean, so that decreased their efficiency again, and that increased expense because they got to pay for those things. And who's going to pay for them? you and you and you and me and everybody that buys the electricity is going to pay for them. You know. So anyway, okay. So we're looking at oxidation of carbon, hydrogen, and possibly sulfur. The steam book has what they call the 3 T's of combustion. And I think I probably mentioned this before, but these are famous in the combustion world. Time, temperature, turbulence. So we got to have fuel and oxygen together for enough time for combustion to occur at a high enough temperature, and the turbulence is the mixing to make sure that we get the oxygen in close proximity to the fuel molecule so that they can react. Okay, table 1. This is pretty good. So I sent this to you. And this is out of the steam book, which you can probably tell by the amount of information on it. And so this is in there. I think it's chapter 10 is their combustion. I'll send you guys out chapter 10, so you can have the whole chapter. We cover a little bit of it, but of course it goes on. As you've seen in steam, it goes on and on and on forever. But this is just some combustion constants. I actually use this table pretty frequently. It's very handy for all sorts of different calculations if you're doing something on a boiler or something to do with combusting fuels. So you can see we've got a substance over there. We start out with, carbon, hydrogen, oxygen, nitrogen, atmospheric nitrogen. Okay, so if you look at N2, we get a molecular weight of 28.0134. N2A is called atmospheric nitrogen. And so what that is that's kind of they've weight averaged the molecular weight to include not the oxygen, but the nitrogen and the trace gases. So there's a little bit of CO2 in there. There's a little bit of argon in there and all that. And so you see the molecular weight goes up a little bit to 28.158. And so when they do combustion calculations, they will assume that the air is oxygen, N2A, and potentially water vapor. That might, if you're allowing water vapor to be in the air. Then we've got carbon monoxide and carbon dioxide in the top 6. And then down here we've got you can read them: methane, ethane, propane, butane, isobutane, and all this stuff, and the formula, molecular weight, and all this stuff. And then okay, so let's go across and look at the columns. We've got the density, and that's at standard conditions of 60 degrees Fahrenheit and 14.696. And the footnotes are down in the table. They're a little hard to read, but you can read most of them. But that's what. So that density is at a standard condition. And then specific volume is 1 over density, just inverted. And then we've got specific gravity relative to air. So is this stuff going to float? Hydrogen's really light. Oxygen's a little heavy. Carbon dioxide is really heavy. It's going to sink. So you can see in the relative to air. Okay, then heat of combustion. So this is BTUs per cubic foot of gas, or BTUs per pound if it's carbon. And some of them, I guess, some of them they do both. Okay, so question, I've got 3 of you I can drill in person. What's the difference between BTUs per cubic foot net and gross? I'm not hearing anything.
Would gross be the total amount you make, and that's the amount you can actually use?
No, that's a good guess. Louder, I can't. I was going to say something similar. Okay. It's higher heating value versus lower heating value. It's the state of the water after you burn the fuel. So now look at carbon. When you burn carbon, do you get any water? No. What's the reaction? C plus O2 goes to CO2. Ain't any water in that. So you get the same number, right? Now, hydrogen, when I burn hydrogen, do I get any water? Yes. What? H2 plus a half of O2 goes to H2O. Okay, what's the state of the water after you burn it? If it condenses to a liquid, then you get the gross or the higher heating value. If it stays in the vapor state, then it retains the energy of vaporization and you get the lower or the net heating value. So see, it's the condition of the water that's created by the burning of the hydrogen. So if you don't have hydrogen, then the number's the same. Look at, see, carbon monoxide, while being deadly, is also a low-grade fuel. Because look, BTU per cubic foot is 320.6. Well, methane, which is basically natural gas, is what? Gross side, it's 1,012. On the net side, if all of the water, H2O stays in the vapor state, it's 911. Well, see, so if you look at the net value, carbon monoxide is what? A third of the heating value of natural gas. So, you know, that's what you get if you don't burn carbon effectively. You know, instead of getting CO2, you get what? You get CO, and you're throwing away a low-grade fuel that, if by the way you breathe it, you know, it'll kill you. So, okay. So you can look at that. So we get BTUs per pound or BTUs per cubic foot. And then we get cubic feet of oxygen into an air that you have to bring in for stoichiometric combustion, for perfect mixing, to burn, like, you know, I guess this is on the carbon, I guess it's a mole, right? Because we got, I mean, a volume ratio is a molar ratio. So, you know, but the cubic foot, it really applies to the gaseous fuels. So if we want to burn a cubic foot of hydrogen, we have to have a half of cubic foot of oxygen because it's H2O, and so it's a half of an O2. Okay. So, and then we also get the flue gas products. So I use this pretty free, and then so you've got the oxygen, the N2A, and then the total amount of air that you have to bring in to get the oxygen. Okay. So, for example, I'll do this with natural gas. If I don't know how much, if I want to estimate how much air is coming through a combustion system that's burning natural gas. Well, if I know how much gas they're using, then I know how many cubic feet, because it's roughly, you know, well, I mean, you've got the number there, a cubic foot of natural gas. If you're using the lower heating value, it's 911. Or that's methane, which is 95% of it, so it's pretty close. And then if you're using the higher heating value, it's 1,000 or 1,012. Sometimes we just use 1,000, but whatever. And so then you can figure out how many cubic feet if you know how much gas. And then for stoichiometric, it's 9.55 or 547 cubic feet of air per cubic foot of gas. And then you can estimate, well, we run about 20-30% excess air. So multiply it times 1.3. So that'll tell you how much air is being brought in through your combustion system to burn that amount of gas. Well, that's a real practical calculation to be able to do. So there's lots of stuff that you can do. But anyway, you have all of these combustion constants available to you. I'm sure there's way more than I can think of off the top of my head. So anyway, that's table 1 that's referred to there in the yellowed notes. Let's see. Well, I tell you, that's pretty much a good time to stop. So we'll just, we'll call it quits there. I'll get this posted to you and we will continue on next time. So again, your next test is a week from today. So be reviewing your boiler and turbine stuff. Hope everybody has a great rest of the day. And we'll see you later.
Dr. Cunningham?
Yes.
Just to confirm, this combustion stuff will not be on the test, will it?
That's correct. It will not. No.
Okay, thank you.